The sun glints off the sleek, reflective surface of the Concorde as it glides gracefully through the upper atmosphere, its engines roaring in harmony. Yet, everything hinges on a seemingly simple mechanism situated at the front of the aircraft, the inlet. Here, as the aircraft slices through the air at more than twice the speed of sound, the inlets operate at the very edge of physics. They perform a delicate dance, simultaneously slowing down the supersonic air and ensuring that the engines receive just the right amount of air pressure to avoid catastrophic failure. Inlet design is one of the unsung heroes of supersonic flight, yet it remains shrouded in complexity, far more intricate than the engines themselves. Why is it that the design of these inlets is more challenging than that of the engines they serve? To unlock this puzzle, we must dive into the intricate world of aerodynamics. What might appear to be a straightforward task, slowing down air, actually involves manipulating shock waves with mathematical precision. Inlets have the daunting task of converting incoming supersonic airflow, which is traveling at speeds greater than Mach 1, down to subsonic levels without causing significant pressure loss. The consequences of a poorly designed inlet can be dire. Just a slight miscalculation in the airflow can stall the engine in a matter of milliseconds, leading to a catastrophic failure. At speeds of Mach 2 and above, the physics of air compression shift dramatically. As an airplane accelerates, air molecules are forced to compact tightly, leading to a substantial increase in velocity and temperature. Ordinarily, air is gradually decelerated to ambient pressure through a gradual ramp. However, at supersonic speeds, there simply isn't enough space for this process. Therefore, supersonic inlets utilize a series of precisely angled shock waves known as oblique shock waves and, occasionally, normal shock waves, which can result in a drastic reduction in air velocity while retaining much of its pressure. To illustrate the importance of maintaining pressure, consider the Concorde once more. The aircraft's inlets were designed to manage airflow at high speeds, ensuring that the engines, Rolls-Royce/Snecma Olympus 593 engines, received air at the ideal rate and pressure for combustion. The Concorde's variable intake ramps not only diverted air but also adjusted dynamically based on the aircraft's speed. As the Concorde transitioned through the flight envelope, these ramps would shift, creating shock waves that were directed away from the engine nose, maintaining airflow without significant loss in pressure. The engineering behind intake design necessitates a comprehensive understanding of thermodynamics. Air, subjected to compression in a supersonic environment, behaves differently than we might expect. Here, let us consider a critical point. At supersonic speeds, whenever air hits an obstruction, it cannot flow around it freely. Instead, this creates a bow shock that reflects back towards the incoming flow, increasing pressure in its wake. If not carefully managed, excessive pressure beyond the engine's capacity can cause flow separation, leading to stalling. To navigate this challenge, engineers rely on strategically designed shock trains, which are a sequence of successive oblique shocks. These shocks allow the air to decelerate, like dragging a heel down a hill, where the weight of the body pushes down in a controlled manner rather than allowing it to tumble uncontrollably downwards. Each shock produces a slight pressure rise while changing the direction of flow, ensuring the air straightens out to become subsonic. A perfect illustration of this design principle is found in the McDonnell Douglas F-15 Eagle, an air superiority fighter that employs similar plug-in technologies to manage airflow. The F-15 utilizes adjustable ramp inlets that shift based on speed and angle of attack, regardless of whether it's engaged in a high-speed chase or a low-speed maneuver. In this case, the inlets can adapt rapidly, transitioning from nearly vertical positions at takeoff and landing to flatter angles during supersonic flight. Here, the inlets function not merely as passive openings but as active participants in managing airflow to the Pratt & Whitney F-100 engines. But, among these myriad complexities lies a common misconception. Many assume that simply having larger inlets or running the engines at higher performance would yield better outcomes. However, this perspective overlooks the crucial aspect of airflow management. An engine's performance is intricately tied to the conditions of airflow entering the combustion chamber. A common false belief is that increased air pressure automatically means more engine power. In reality, engineers must design inlets to harness air efficiently, managing not just quantity but quality. What happens when inlets are improperly designed? Consider the case of the Lockheed Martin F-22 Raptor, an advanced tactical fighter widely celebrated for its stealth and agility. However, during early testing, certain variants experienced inlet designs that led to airflow separation at reduced power settings. This failure disrupted the airflow required for optimal engine performance, causing engine stalls that impeded the aircraft's high-altitude, high-speed capabilities. Engineers soon recognized that the shapes and angles of the shock waves generated had to be tightly controlled, not only to sustain performance but also to ensure lifelike responsiveness during complex maneuvers. As we delve deeper, an aspect of the inlet's design emerges that many do not often consider: the role of variable geometry. The oblique shocks necessitate flexibility. A fixed structure would offer limited adaptability, susceptible to the rapid changes in airflow pattern during flight maneuvers and engine performance adjustments. Excellent examples of variable geometry inlets are found in the MiG-25 Foxbat, an aircraft initially shaped under the Soviet Union that could reach Mach 3. This plane adopted movable components influenced by both speed and altitude. Designed with an adaptable intake that could adjust in real time, the MiG-25 showed that the proper manipulation of airflow could yield an aircraft capable of escaping defense systems that were state-of-the-art at the time. Halfway through our exploration, one could pose an engaging question: which of these aircraft would you least want to stand next to during takeoff, the intensely powerful Concorde, the agile F-15, or the rapid MiG-25? Each represents the marvel of aerospace engineering, yet each is tied intimately to how inlets are intricately designed to manage their immense capabilities. Understanding the inlet dynamics is crucial in appreciating the brilliance of engineering at play. Upon reflecting on these challenges, one key takeaway emerges: successful supersonic fleet operations hinge upon manipulating pressure waves rather than simply managing airflow. This nuance is vital in the engineering of inlets. The notion that more air leads to more power is misleading. Instead, successful designs hinge upon managing air pressures and leveraging shock waves, tools to guide incoming flow. Concluding our journey, we recognize the profound ingenuity that resides within our contemporary aircraft. Supersonic inlets, often overlooked, hold the power to dictate the operations of entire generations of flight. Without them, cutting-edge jets would falter in an unforgiving atmosphere, potential casualties of an inadequate airflow. Remember, the bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you. The relationship between an aircraft's engine and its intake is one of critical dependency. When we think about aircraft inlets, it becomes clear that they are not simply passive ducts allowing air to flow into the engines. They are dynamic systems executing intricate aerodynamic behaviors. Here, we will delve further into the design considerations and operational intricacies of supersonic inlets, revealing the myriad ways they shape flight performance. Let's first revisit the mechanics of shock waves. Shock waves are abrupt changes in pressure and velocity in a fluid, and they serve as vital components in managing airflow at supersonic speeds. When the air traveling towards an aircraft's inlet reaches supersonic speeds, it creates a series of interacting pressure fronts, what we call shock waves. These waves come into play as the inlet guides the incoming air through a carefully orchestrated series of oblique shocks, rather than allowing a gradual deceleration through a standard duct. As an illustration, consider the Boeing X-43, an experimental hypersonic aircraft that achieved a speed of Mach 9.6. The unique airframe of the X-43 incorporated a scramjet engine, which relies on the principles of supersonic combustion. Here, the air meets the inlet of the craft at speeds exceeding Mach 3, and the precisely engineered ducts deliver air at a suitable pressure for combustion. The shock waves in the inlet of the X-43 were the key feature that enabled it to transition from supersonic to hypersonic speeds while managing temperature and flow conditions. But achieving this transition isn't without its challenges. The design must not only allow for flow stabilization but also compensate for varying conditions such as altitude and angle of attack. As aircraft move between atmospheres and speeds, air density fluctuates, introducing additional stresses on the inlet. For instance, in the case of the Lockheed State Route 71 Blackbird, with its operational ceiling approaching 80,000 feet, its dynamically adjustable inlets had to deal with variable air conditions while ensuring optimal engine performance. The SR-71's inlets featured a unique design with moving ramps that adjusted the angle of attack and airflow depending on flight conditions. This design also manages the friction-induced heating encountered at such speeds, allowing for sustained operations in extreme situations. When we look at the durability of these components, materials stand out as a crucial element in inlet design. The requirement to withstand heating often leads engineers to choose advanced materials such as titanium and carbon composite fibers. For instance, the inlets of the F-22 Raptor combine stealth technology with high-temperature composites that effectively minimize radar signatures while delivering necessary airflow to the engines. This remarkable integration of design and materials elevates the performance parameters of such advanced fighters. Another example of addressing airflow management through innovative engineering is showcased in the Airbus A380, the world's largest passenger aircraft. Even though the A380 operates at subsonic speeds, its design integrates principles evident in supersonic technology. The leading-edge slats on the wing can be compared to the functions of an inlet, as they serve to manage airflow over the wing during takeoff and landing, thereby enhancing lift while preventing stalls. This showcases the necessity of airflow management across various categories of flight, not just supersonic transport. When we discuss the challenges associated with inlet designs, one cannot ignore the influence of turbulence. At supersonic speeds, the abrupt transitions in air pressure can generate turbulent flows, especially during challenging maneuvers or atmospheric disturbances. An innovative approach to minimizing such turbulence in transverse inlets involves using perforated plates or screens to condition the incoming flow, smoothing out the transitions before they reach the engine. This nuanced engineering decision helps maintain engine performance and stability throughout various operational conditions. As we have seen, inlets are not just about controlling the pathway for air, they play a pivotal role in shaping the entire operational efficiency of an aircraft. The variable ramp inlets of the Concorde serve as an excellent case study. When cruising at speeds near Mach 2, the variable ramps effectively modulated air intake to mitigate the risk of shock-induced stalls, maintaining engine stability and performance. During ascent, the ramps would create a turbine-like environment that channeled the airflow in such a way that the engines continuously received the appropriate air pressure and volume for efficient operation. Moreover, shock wave management through airflow shaping is also critical in unmanned aerial vehicles, particularly when considering their operational effectiveness in both military and civilian domains. UAVs like the Northrop Grumman Global Hawk utilize inlets that are keenly designed to maintain optimal air pressure, thereby enhancing fuel efficiency while maximizing the mission's range. The versatility of inlets in terms of sizing, shaping, and adaptability is thus a recurring theme across many platforms, reflective of the broader requirements of modern aerodynamics. Now, transitioning from design principles, let's evaluate the implications of these complex systems on mission outcomes. The interplay between inlet design and engine performance directly influences aspects such as fuel efficiency, operational radius, and even weapons delivery. For instance, the Boeing 787 Dreamliner features advanced inlets designed to optimize the airflow to its engines, leading to a comparable 50% improvement in fuel efficiency compared to earlier models. This substantial optimization is particularly imperative under the current global focus on sustainability within aviation. Now, we face another misconception prevalent among aviation enthusiasts, the idea that all supersonic inlets work identically. In reality, designs are tailored to specific operational envelopes of the aircraft. One only needs to examine the contrasting approaches of the Concorde and the State Route 71 to see how remarkably different inlet designs can be, driven by their unique mission requirements. The SR-71's inlets are robustly engineered to handle extreme speeds with an emphasis on high-altitude performance, whereas the Concorde's inlets focus on the optimization of fuel efficiency and performance over varying subsonic and supersonic phases. This differentiation highlights how engineers must operate within a twofold constraint of performance and safety. Just as a race car's aerodynamic features are tuned for faster laps, the inlets of supersonic aircraft are invariably conceived to balance top-end performance while ensuring the aircraft remains controllable and safe throughout its operational envelope. This nuanced understanding of performance helps explain why, in many cases, the inlets are often described as the heart of supersonic flight. Reflecting upon the complexity and elegance of these systems in aerospace engineering brings us to a point of appreciation for the meticulousness behind each design choice. Inlet designs, from the simplest to the most complex, can illuminate our broader understanding of engineering as applying theoretical principles under the constraints of real-world conditions. In conclusion, as we explore the symbiotic relationship between air and engine, we recognize that maintaining momentum while dissipating energy is a delicate balancing act that defines supersonic flight. In the various examples we've examined, the intricate interplay between airflow and aerodynamics is foundational to maintaining efficient and stable flight. The sheer scope of engineering challenges met through innovations in inlet designs exemplifies human ingenuity. Countless hours of design, testing, and refinement work to ensure that each machine fulfills its intended purpose with elegance and efficiency. As we conclude our in-depth examination, let us remember that every aircraft is a marvel of engineering, not merely for its size or speed, but for the unseen intricacies that make its flight possible. Whether pulsing through the sky on a supersonic jet or cruising at a steady altitude in a jumbo airliner, the designs we rely on demand a deep understanding and respect for the physics at play. The bigger the machine,